Okay, welcome back again. This is Chem3202 course overview review. And today we're going to be looking at the Unit 2, Section 3, Lesson 2. We're looking at a titration material, and this is based heavily on the core lab that you would have to do for this course called the titration, the acid-base titration lab. So let's have a look at the acid-base titration. If you want some background reading and information on this, you can see this in your textbook as well. Page 603 to 605, and there's a little talk here on page 838 regarding precision, errors, and accuracy that might be involved in this particular setup. There's a couple questions that you can have a look at here on page 616 as well, and of course lab number 3 is dealt with the technique and materials and whatnot are dealt with on page 606. So you may want to familiarize with that lab on page 606. Here are the outcomes for this lesson. This is what you're expected to know. And here we go. Here's a little cartoon that reflects a little bit of what titration is all about. So here we are, World War I, I guess. Despite the heavy flak, McAllister's aim was true, and his carefully measured aliquot of hydrochloric acid found its mark deep in the enemy reservoir of sodium hydroxide. Now, a measured aliquot is a very, very precise measured amount. In this case, it's a very precise measured amount of hydrochloric acid. It's going to be delivered to try and neutralize the enemy base, and of course, once he's successfully done that very carefully, his comment is, he grinned wryly, finally one of the enemy's strongest bases has been completely neutralized. So that's our task here in titration, to be very, very precise in our aim, be very, very precise in what we're doing. We want to be able to try and neutralize an unknown compound, and by knowing by using a precise amount, we can do a few calculations here to try and figure out the concentration of an unknown acid or an unknown base, depending on what we're trying to do here. So let's have a look. Okay, so here's the setup for a titration experiment, and we're looking at this, and we're going to be using a very precise glass or plastic burette, and it has graduations marked on the side, and you actually fill it up with the standard known solution. So you're going to be given 2 solutions in your lab. One substance, you know everything about it. You know its identity, you know its concentration, and you're confident that the concentration is what it says it is on the bottle. So that solution, the one that you know everything about, generally always goes in the burette. Okay? The one that we don't know the information about, the one that we're trying to find the concentration of, or unknown, that one always goes in the Erlenmeyer flask or the beaker at the bottom. Okay? This burette has a drain valve here, which we can very accurately, very carefully start adding or mixing these two together. And we can record a measurement before, which is going to be our initial volume that we started with, and we're going to measure a volume once we finish the titration. So we have 2 volumes, we subtract the difference, and we know exactly how much of that solution we added. So a few definitions that go along with this acid-base titration. The definition titration itself is simply saying it's the slow progressive addition of one reagent or reactant to another. In acid-base chemistry, what we're dealing with here, that one solution is going to be a strong acid, and the other solution could be a strong acid or a weak base, sorry, a strong base or a weak base. So one of these guys is generally going to be a strong acid or a strong base. Typical titration involves adding a solution of known concentration from this point forward to be known as the titrant, all right, not the tyrant, the titrant, okay? So the titrant is the one that we know the information about. So the known concentration is always going to be the titrant. The unknown or concentration is what's going to be called the sample. All right, so the one that we don't know the information about, or the concentration, is going to be called the sample. There we go. So it's the titrant is the known, the sample is the unknown. We're going to add just enough titrant here to completely neutralize the unknown sample. Now, in order to do that, we have to have some kind of visual cue. Because if we're adding, say, sodium hydroxide to hydrochloric acid sample, sodium hydroxide is clear and colorless, just like water. Hydrochloric acid is clear and colorless, just like water. And when they react together, we're going to get sodium chloride aqueous and H2O. Both of these products are colorless as well. So we have no idea when to stop here if we were doing this experiment. So what we have to do is we have to add an indicator, an acid-base indicator, as we talked about in the last lesson, that's going to change its color when we're at or very close to the equivalence point. Now this is another definition here, the equivalence point. This is the point at which chemically equivalent amounts of titrant and sample have reacted. So mole equivalence. So the number of moles of OH is equal to the number of moles of H3O+. And that's what we're talking about at the equivalence point. So I'm just going to jot that down here. So at the equivalence point, the number of moles of OH minus is equal to the number of moles of H3O+. So we've completely neutralized the acid or the base. And we call that the equivalence point. Now, the indicator that we're going to use here is going to be one that is going to be able to change its color somewhere very, very, very close to where the pH of the equivalence point is. And we'll talk more about that later. All right? But in any case, we get a visual cue of when we've added equivalent amounts of acid and base by looking at the color change of the indicator, and we're looking for the equivalence point. So here we go. We're adding just enough titrant to completely neutralize the acid or base, and we say when this amount is there, we want to be able to detect it, and we call this the equivalence point. And we're saying that the equivalence point is generally where the moles of H3O+ is equal to the moles of hydroxide. We looked at that. For a strong acid or a strong base, this occurs very close to pH 7, but only pH 7 if we have a strong acid like hydrochloric being neutralized by a strong base like sodium hydroxide. For any other combination, if we had a weak acid like vinegar and a strong base like sodium hydroxide, the pH is going to be different than pH 7. So it's not always pH 7. And that's a big misconception that people have, that every time we do this titration, equivalence is going to happen at pH 7. It's not true. It depends on what you're neutralizing. So what we need to do is look at what's called the end point. And the end point is slightly different than the equivalence point. The equivalence point we really can't see. The end point is the point at which the indicator changes color. So we call that the indicator endpoint. And it's going to be slightly different than the equivalence point because not very many indicators ever change color at pH 7. All right, phenolphthalein is the one we like to use, and remember that changes its color at about pH 8.2. So what we like to choose here is an indicator that changes color as close to an equivalence point that we have as possible. So if we're doing a strong acid with a strong base, we know that in this situation the pH is going to be very close to 7. So when we pick an indicator, we have to make sure that the indicator changes color very close to pH 7, around pH 8, pH 6, like that. If we had an indicator that changed color at, say, pH 2, that's way too soon. Or if we had an indicator that changed color at, say, pH 10, that's way too late. So we want to get an indicator that changes color very, very close to the endpoint or the equivalence point. And in order to do that, we want to minimize any error. And we're going to talk about that in the next lesson when we look at titration curves. So I'm going to leave that at that for now. Okay. In this experiment that we're doing here, we're going to be using phenolphthalein. And remember, phenolphthalein changes from colorless to pink at about 8.2. So as you're doing your titration experiment, let me just go back for a second. You're going to be adding, this is going to be our acid down here, which is going to be colorless to start. We're going to be adding some sodium hydroxide. And as we add it, we want to swirl and mix up the solution to make sure that everything is homogeneous and everything is mixed perfectly. So what's going to happen is as the sodium hydroxide drops out here, this is going to cause the phenolphthalein to start turning pink. And as you swirl it, of course, the pink fades because we're mixing it up nice and even. But as the pH begins to rise, now at 8.2, we're already gone past the equivalence point. Because remember, for a strong acid and a strong base, the equivalence happened at 7. But changing at 8.2, if we stop when it's very, very, very bright, very, very light pink, then we're closer to pH 8.2. If we continue to put sodium hydroxide in here, the color is going to get real dark. And the darker it gets, remember, means that the equilibrium is going way beyond, and it's favoring the products, and it's going to be really, really dark, and the pH is going to be up around 10, which is way too far. So for phenolphthalein, we still want to be careful that we stop it real early so that we get this light pink and not the dark pink. If it's too dark, that means we're gone way, way beyond. We've added way more than we need. All right, we're gone beyond the equivalence point. That would be a source of error in your lab. Another thing we have to look out for in this particular titration, acid-base titration, is the idea of standards. When we talk about standards, we always need something, a benchmark to compare something to. It's no good to do a measurement if we have nothing to compare it to. So you might say, well, you know, I'm a fast runner. I can run 5 kilometers in hour and 45 minutes. And you might say, well, sure, that's not very fast. I can go better than that. You need something to compare it to. I need some kind of standard. If I'm going to say I'm fast, I need something to compare it to. So we have to develop standards here to say, okay, what is this concentration? Is it precise? Is it accurate? Is it exactly what we're measuring it to be? All right, do we have something to compare it to and say that it's precise? So a standardized solution then is one of these that we know exactly what the concentration is. And it's very carefully arrived at, and everything is done perfectly, and we know exactly if it's written on the bottle that it's 0.100 moles per liter, then we're confident that it is that concentration. But that's not true for all solutions. Some solutions are not good for being standards. All right, they're like me as a runner. I'm not a very good standard because I'm not very fast. All right, in this case, hydrochloric acid is not a good standard. You may go to your chemical cabinet and find hydrochloric acid on your shelf there, and it says 0.100 moles per liter, and you say, yeah, that's perfect. No. The problem is hydrochloric acid is created by bubbling hydrogen chloride gas through water, and when it ionizes the water, it dissolves. What happens is if the cover is left off the hydrochloric acid, it does something like a can of Pepsi or a bottle of Coke or something when you leave the cover off it. It goes flat. The hydrochloric acid, the equilibrium is going to favor the hydrochloric acid returning to the gas phase, and it's going to start to escape over time. So over time, the hydrochloric acid becomes weaker and weaker and weaker and weaker. And just because the label says 0.100 moles per liter, it depends on how old that hydrochloric acid is, how long it's been on the shelf, how much it's been used, how many times the cover's been left off it, and things like that. We really can't control that. So hydrochloric acid is not a good standard. So we would not be able to use that in the lab and be very confident in our final results. So that's no good. Sodium hydroxide is another one that we like to use, but it's not a very good standard. And the problem with sodium hydroxide is it's something called deliquescent or hygroscopic, which means in the solid form, sodium hydroxide begins to absorb water. It begins to hydrate. It absorbs water from the air. And if the cover is left off the sodium hydroxide for very long, the sodium hydroxide can actually absorb so much water that it actually dissolves itself, and it gets very clumpy and starts to get thick, and all the crystals begin to stick together. And the problem with it is that when we go to weigh it out to make a solution, so if we need to make a 1 mole per liter solution, we need to weigh out 40 grams of sodium hydroxide. So if we're not sure what the degree of hydration is, then how can we be 100% sure that we just weighed out 40 grams of sodium hydroxide? Perhaps we just weighed out 36 grams of sodium hydroxide and 4 grams of hydrated water that's stuck to the crystals. We can never be sure of its level of hydration. So because we cannot be sure of its level of hydration, we can never be sure 100% of its actual purity. So for that reason, sodium hydroxide cannot be used as what's called a primary standard. They have problems. We have issues with these guys, and that's the issues. So these guys cannot be used straight off the shelf because we're not sure of their concentrations. All right? Now the question is then, well, why do we like to use it? Well, we like to use these guys because they're monoprotic, which means they only have 1 hydrogen to donate in the case of HCl. The strong base sodium hydroxide is monobasic. It only produces 1 hydroxide, not like something like calcium hydroxide, CaOH2, that would produce 2. So because these guys are monoprotic, it produces 1 hydrogen, and this guy would produce 1 mole of base. It makes the stoichiometry calculations easier. The mole ratio is going to be 1 to 1. So we like it for that reason. And the other reason we like these guys is because they're really relatively cheap. We can get them everywhere. and they're readily available. It's easy to get, and we can get our hands on it real easily. All right, so that's a good reason. So we still like to use these guys even though they got problems. So what we have to do then is we have to standardize them. All right, we have to go and see if we can measure what their current status is. If we take the hydrochloric acid off the shelf and we're not sure of what the concentration is, what we have to do is standardize it so we can actually measure the accurate percentage or the accurate concentration of the acid. And what we have to do with that is we have to do a titration experiment, like we're going to do, with what's called a primary standard. And primary standards are these substances that are 100% pure, regardless of if we leave the cover off them and store them overnight, or if we have them stored in the chemical cabinet for 2 years or 5 years or whatever. Every time we go to them, we know that we're confident that they're going to be 100% pure. And some of these examples would be things like hydrochloric acid is going to be standardized by using some sodium carbonate. Relatively cheap, easy to get. Sodium carbonate, it doesn't hydrate, it stays dry, it doesn't absorb any water. So if I go out and measure out 4 grams of sodium carbonate, I know that I've got 4 grams of sodium carbonate. There's no water hydrated with it. So that's what we use to make a solution. And then we would use this to try and figure out the concentration of our HCl that we have on our shelf, and thereby we can get an accurate measurement of that. Other ones here, bases. Things like sodium hydroxide, we can make up a solution of sodium hydroxide, but we're not sure of what its concentration is because of all that hydration. What we can use is what's called potassium hydrogen sulfate. That's a very pure solid that stays dry. And the other one here is what's called potassium hydrogen phthalate, and you would see it called KHP. That's another very pure substance that doesn't hydrate, that stays very pure over long periods of time, so we can accurately measure it. And if we can actually measure the concentration of this guy, then we can use that to accurately measure the concentration of sodium hydroxide. And once we know the accurate measure of sodium hydroxide, then we can use the sodium hydroxide in our experiment. So we would have to standardize them before we use them. Okay? And this is why they're so good, because they don't absorb any water and they stay pure. Now, there's some drawbacks of these guys. Some of these things like KHP can be very expensive. And you know, for us in a high school chemistry lab, we don't want to spend a whole lot of money on these things. So we would want to use the cheaper ones. And the other thing here is that these guys are generally weak acids or weak bases. And that makes titration problematic because we no longer titrate a strong acid with a strong base. Now we start looking at various indicators. We got to start changing our technique a little bit because the equivalence point is no longer going to be pH 7. So we have to take that into account when we start picking the indicator that we're going to use. And again, we'll talk about that in the next section. Okay. So 3 things that primary standards have to be. If you're going to use something for a primary standard, it generally has to be easily measured. So solids would be the best bet there. They generally have to be highly soluble in water. We don't want to start interfering the reactions with something that's not going to dissolve completely. Then we start getting into problems of percent reaction, things like that. Our calculations get complicated. So we would want something like a sodium compound or a potassium compound that would be 100% soluble. And number 3 there, of course, the high level of purity is a must. It has to be very pure and non-hydrated in order to be a primary standard. So there we go. So in our experiment then, we're going to assume that I'm going to use some sodium hydroxide with some unknown vinegar. We're going to actually go to the store and get some packets of vinegar, and we're going to actually measure the concentration of the vinegar that would be in these little packets, okay, or some household vinegar that you might have. So assuming that we're going to use sodium hydroxide as our titrant, this is the one that we know the accurate concentration of. That's the one that goes in the burette. And we generally fill it up using a funnel. Be careful not to spill. And we generally overfill it a little bit, and usually what happens is there's bubbles that remain here, and you're going to have to turn the drain valve here to try and get the bubbles out, and that's why you would put a little extra in here. All right. Now before you fill it up, I'm skipping a step here. Before you fill it up with the sodium hydroxide, what we want to do is make sure the burette is rinsed with soap and water, and then rinse with water several times to get rid of all the soap. We want to make sure that this is clean. And once we rinsed it with some water several times, we want to rinse it with our sodium hydroxide just a little bit, because if there's any water that's inside the burette, we don't want to dilute our standard solution. right? We don't want to do anything here that's going to jeopardize our purity that we just found out what it was. It was 0.100. We don't want to jeopardize that by contaminating it with dirt, or if there's any water left here after rinsing, we don't want to dilute our solution, because if we do that, we won't know, our calculations will not be accurate. Okay, so we do that, then we fill it up with some sodium hydroxide. Okay, we would release a little bit in a waste beaker to get rid of the air in the valve. Okay, number 2 there. Okay, the next thing we have to do here, what are we doing? We're going to get a sample of vinegar here now, and we're going to use a delivery pipette here. And it's going to be very accurate, 10.00 mils. Remember, we talked about this as being a very accurate aliquot. All right, it's an accurate measurement. And you guys did pipetting, of course, in 2202, so I don't have to review much of that here. But the same thing applies here. We're going to take some unknown vinegar, and we have to rinse out this glassware with soapy water first, rinse it several times with water. And then in order to get rid of any water that might be here that could possibly dilute our vinegar, we need to pull up a little bit of vinegar and then rinse this out and throw that away, because that could possibly be diluted. So we want to get rid of that. Again, we don't want to do anything here that's going to jeopardize our accuracy and our final result. Okay, there we go. We know that when we start pipetting and when we measure things with glassware, we look at the bottom of the meniscus. So when we make a measurement, we always make sure the bottom of the curved surface of the water is touching the line. Okay, so that's going to be a line that's okay, on the glassware, and you make sure the bottom of the meniscus just touches that line. Okay, so what we do then is we have to make sure that we add our indicator, very important, because if we don't add our indicator to this beaker, we're going to transfer this vinegar over here. We have to make sure we add our indicator, because if we don't, we won't see anything happening. Remember, it's the indicator that gives us the visual cue that we're near the equivalence point. Okay, we're near the point where the acid and base are neutralizing. Okay, and this is a general idea of how this is going to work. You're going to slowly add, you're going to start, stop, start, stop, start, stop, slowly add, swirl, and then you're going to stop just when the phenolphthalein starts to turn a light pink. If you go dark pink, then you're too far. You overshot the end point. What you have to do is throw this away, start again. Okay, as you start titrating, what you're going to do is you're going to measure the initial volume. We record this in a table. This would be the initial volume. And as you start adding your sodium hydroxide, you go slow, slow, slow. And as you start adding, all of a sudden, the color starts to change. You swirl, it fades, and then you start adding a few more drop by drop by drop until eventually you get that nice light pink color, and then you stop. And now you have a place where you started and a place where you finished. The difference here is the volume of sodium hydroxide that you added. Okay, here we go. So when we measure this, we always read the burette from the top down. It starts at 0, it reads down to 50. So if this was my measurement here in blue, I would read this down and say 12.1234. It's not quite 12.5, it's somewhere in between, so this is going to be 12.1234 and a half, so 4.5 right there. Now we got to watch out for parallax. And what parallax is an error in measurement from looking at something from an angle. And the idea behind this is this is your eyeball right here. I'm poking you in the eye now. Ooh, that hurts. Ooh, that hurts. Ooh, ooh, ooh. Right? We're poking you in the eyeball here. We want to look straight across because that's where we get the straight measurement. If I look at this from an angle, so if I'm looking at it from the top down, what's going to happen is my eye is going to look in a straight line, and here's where I see it. But as my eye continues on to do the measurement, I'm actually going to read more because it's closer to 13 than I actually used. And if I look at this down, if I'm sitting down on a bench and looking up at the burette, okay, again, I poke you in the eye. If you're looking up, then your eye is going to track up, and you're not going to read enough. So you're going to read less than you've actually added. So that would be parallax. And what you guys need to do is make sure you, if you're standing up or sitting down or whatever, make sure you move the burette so that the meniscus is right at your eye level, straight across, and get a nice accurate reading. There you go. The other thing, of course, is you're always going to read the burette from the top down. Okay, it starts with 0 and it goes down to 50. There we go. Okay, here's a possible calculation that you can do. This is going to be some information that you're going to collect. So in this case, we're going to take 10 mils of acetic acid, and we're going to titrate it against or with some standard sodium hydroxide. Now you notice we don't know the concentration of the vinegar. We do know the concentration of the sodium hydroxide. We do 3 trials because we want to try and get the best that we can. We always measure the initial and the final and we record it. In this case, the first time we did it, we've got a difference of 15.55 milliliters. Okay, not bad. But generally the first one is a fact-finding mission. All right, you're trying to find your range. It's like throwing darts or horseshoes or something like that. The first one is usually way out to lunch, and you say, well, okay, now I know where I got to throw it. So what happens is you would omit the first trial and say that's only a trial run, and what you're trying to do is to get 2 readings. So this is trial number 2 and number 3. You want to get 2 of these guys that agree within plus or minus 0.1 of a milliliter. So it can't be outside of that range. You notice that this guy here is 15.5. Well, that's different here by 0.4. That's way too far away. 0.5 and this guy's 0.16. Again, that's almost 0.4. So this one's way out of range. But you notice that these guys, 0.12 and 0.16, their difference is 0.04. They're close enough. They're within the range. Okay, so what we need to do now at this stage is say, let's do the calculation that goes along with this. So what we want to do here is we're going to take all the trials that agree within 0.1 of a mil, plus or minus. It can be higher or less than 0.1. We're going to add these guys together and take their average. And this is going to be the volume of sodium hydroxide that we're going to use to calculate our concentration of vinegar. So here we go. We now know our volume of sodium hydroxide. We're going to do our calculation here. It's a neutralization reaction. Okay. We know the volume of sodium hydroxide. It's the average volume. We know the concentration of sodium hydroxide. It's this standard 0.1404. Very accurate. Look at that. 4 digits of significance. We know the volume of acetic acid we use. We use a 10 ml pipette. Very accurate. Right? We were very careful. We used the perfect aliquot. We just don't know the concentration of this. So this is some simple stoichiometry here now, where we can calculate the number of moles of sodium hydroxide, N equals C times V. We put our values in, calculate it, very accurate now, it's 4 digits. All right, so we get 0.002126 moles of sodium hydroxide. The next thing in stoichiometry, of course, is the mole ratio. And in this case, it's a 1-to-1 ratio, 1 to 1. So the number of moles of vinegar is equal to the number of moles of acetic acid. That was the equivalence point. Remember? Equivalence point. That's what we were looking for. That's the purpose of the titration. Equal moles of acid and base. Now that we know the number of moles of acetic acid, now we can calculate the concentration of acetic acid. C equals N over V. We take our number of moles here, divide it by this. Now look at what we got done here. 10 milliliters, we need to divide by 1,000 to get liters. 0.0100 liters. We do our calculation, 0.2126 moles per liter of acetic acid. There we go. So what we just did here was a titration stoichiometry calculation. On the public exam, you notice here 4% for this, 4% for this question. You have to do 4 things. The very first thing they're going to give you a mark for is the fact that you averaged only 2 of these. You said something to the effect that you're going to omit that one. All right, so you would say something to the effect that you discard your trial run. You take your average, that's 1 mark. 2 mark, well, another mark for this calculation, another mark for this calculation, and 1 for this one. They may even give you a mark here or half a mark if you write your equation out and state your knowns, right? So marks for process, final answers, okay, but marks for process. Watch your significant digits. This question has 4. So your final answer should have 4. And there we go. Okay, here's another public exam question. This guy here this time is titrating some known sodium hydroxide with 25 mils of sulfuric acid. So once again, the first run is generally a trial run. Remember, it has to agree within plus or minus 0.1. This guy is way out. This is out by 3 milliliters almost. Too far. So these guys agree within 0.1. The difference here is 0.05, so that's good. So the very first thing we have to do here is calculate our average. and that's the average volume of sodium hydroxide we're going to use. Now this question is a little bit different. This question is using sulfuric acid, and in this case there's two hydrogens that have to be neutralized. So in this case we have to look at this and say the ratio now is going to be 2 to 1, because we're going to completely neutralize the sulfuric acid. We're going to get Na2SO4. So you got to watch that. It's a 2 to 1 ratio, which means now we needed to use twice as many moles of sodium hydroxide than sulfuric acid. So here we go. We write down what we're given, what we need to find. We know the volume of sodium hydroxide. We just found it here. It's the average volume. We know the concentration. It was given. 3 significant digits. We know the volume of sulfuric acid. It's 25 milliliters. 4 significant digits. We want to find the concentration. Same as yesterday. Same as the last calculation. First thing we want to do is find our number of moles. N equals C times V for the sodium hydroxide, because that's what we know. We put our values in. We get 0.00163 moles of sodium hydroxide. Now we have to do our mole ratio. In this case, the mole ratio is required over given. This is what we're given. We know everything about this, so this is my given. This is what's required. So the mole ratio is required over given, so it's 1/2. So we need half as much sulfuric acid to neutralize 1 mole of sodium hydroxide. That works out to be 0.0006314. And now the final calculation. We want to find the concentration of our sulfuric acid, so C equals N over V. We do our calculation here. Again, changing our 25 milliliters to 0.025 liters by dividing by 1,000 there. And I get 0.0252 moles per liter of sulfuric acid. Okay? And you can see here, well, it depends on the volumes too. But anyways, this is a typical question that you would get on a public exam. We're 3 marks. And again, probably 1 mark for this business right here, and another mark for this calculation, and the fact that you recognize it's a 2 to 1 ratio. Okay? So be careful with that. All right, with that said, now I'm finished. Take advantage of our online tutors, and there's lots of public exam questions on this. If you have any questions, don't hesitate to drop one off in the discussions, and I can try and get back to you, or the tutor can get to you, and we'll help you out. So don't forget now, lots of stuff there for you guys to utilize. Okay, see ya.